Hey guys, Miss Marusik here, and in this video we're going to do a review about atomic structure as well as refresh our memory about calculating average atomic mass. Now, I know a lot of you probably remember some of this stuff from pre-AP. I just thought we would do a quick little review of it since we've all slept since then. Summer's been in between, a lot has happened, so I thought it couldn't hurt to just make sure that we all feel good with this information. I've gone ahead and filled out a few things here about protons, neutrons, and electrons that you probably remember. Protons have a positive charge. They're found in a nucleus. If I change the number of them, I end up creating a different element. As a reminder, elements are defined by whatever their atomic number is. And atomic number helps us to figure out, do I have hydrogen or helium or argon? What element do I have? And atomic number is defined as the number of protons inside of that element. So just as a reminder, on our periodic table, we can define those atomic numbers above each of our elements. So you see here, hydrogen has 1, beryllium has 4, calcium down here has 20 above it. That's just telling us those number of protons that are present. Next, we have neutrons. Those are neutral. They're found in the nucleus. If I change the number of these, I keep the element the same, but I change what isotope of that element I have. As a reminder, we have something called mass number. Mass number is the number of protons and neutrons added together. It tells us what specific isotope of each element that we have. And so if I change the number of neutrons, I also change what that mass number would be. Finally, here we have electrons. They're negatively charged. Instead of just saying they're found in the electron clouds, I got a little bit more formal here and said that they're found in the orbitals. As a reminder, we have those sp, d, and f shaped clouds that hang out around the nucleus, and those are called orbitals, and those are where our electrons can be found 90% of the time. And if I change the number of electrons, I end up creating ions. As a reminder, ions have a charge associated with them, so they're no longer electronically neutral like an atom would be. Out of the 3 subatomic particles, which are approximately the same size and mass, those would be our protons and our neutrons. Out of the 3 particles, which is the smallest, that would be our electrons. And to give you an idea of the size differentiation here, protons and neutrons are about 1,000 times bigger than electrons. So electrons are very, very small, but they're just as negative as protons are positive. So I kind of joke that they pack a lot of punch for their size. Out of the 3 subatomic particles, which is responsible for the identity of the element, as we've already talked about, that would be our proton, as that determines our atomic number. Atomic number here, again, that's our number of protons. Mass number, as we've already talked about, is defined by protons plus neutrons added together. So notice that electrons don't factor anywhere into that identity because, again, we could have lost or gained those electrons, and so I could have created some ion. If an atom is neutral, the number of protons is equal to the number of electrons. So again, something that I see students mess up a lot is they think that proton and neutron count are equal. And that is not the case. We have to be really careful. The only time we can assume that numbers are equal is if I have an atom, I can assume that the proton and electron count's the same. Now, if I had an ion instead of an atom, I can no longer make that assumption. So we have to be really careful there too. I would have to be given some other additional information in order to figure out my neutron count. I could not do it strictly based off of proton and electron count. I would need more information. If I did have an ion instead of an atom, a positive ion is called a cation, while a negative ion is called an anion. And a funny, cute little way to remember this, it's kind of dumb, but it totally works. If you think of this T in the cation as being like a positive sign, because it kind of looks like that, I see, like with my eyes, I see a positive ion. Isn't that cute? I see a positive ion. All right, and then it kind of works for anion too. Watch this. I have a negative, and for negative, ion. See? So that way, instead of just calling it an ion, we can specifically call our ion a cation or anion and give somebody a little bit more information about it. Now, for real quick, I do want to talk about cation and anion formation. All the time I see people put on things that if I change the proton count, then I can form an ion. But that's not the way you want to form an ion, because that would actually change what element I have. So instead of changing proton count, I want to make sure that anytime I'm talking about ion formation, that I'm talking about changing electrons. So it asks, how is a calcium ion formed from a calcium atom? Well, in order to get more positive charge than negative charge here, that means my proton count would need to outnumber my electron count. So what that means is that I would need to lose 2 electrons here. On the flip side, if I end up with a negative charge, what that means is that I need negative electrons to outnumber my positive protons. So to do that, I would need to gain 1 electron. Now, in pre-P, we talked a lot about this nuclear symbol format. It kind of gives us a lot of information about an element all at once. So you notice here our X represents our symbol. A, as defined further up here, was our mass number, so that bigger number goes on top. Z on the bottom is the atomic number, so our proton count goes below. And then if we have a charge, if we have a cation or anion, I would put that charge there. If I have a neutral atom, I would just simply leave that blank. So let's do a couple of quick examples here. It wants us to write the nuclear symbol and something called the hyphen notation for an atom that has an atomic number of 9 and a mass number of 19. How many electrons and how many neutrons does this atom have? Well, first off, I see that I have an atom, which means that I don't have a charge, that it's electronically neutral. So what that means is that I automatically know that my proton count should be equal to my electron count. So that's going to come in really handy for us here in a bit. I also see that I have an atomic number of 9, and as a reminder, that would be my proton count. So if I go now look at the periodic table and go find the atomic number of 9, I see atomic number 9 would be representative of the element fluorine. So I know off the bat here that I have fluorine. I also know that the number down here should be 9. I also know that I can leave this top corner blank because we said it was an atom, meaning it's neutral. Okay, and then if I keep on reading, it tells me I have a mass number of 19. So what that means is that 19 goes up here on top. So there is my nuclear symbol. Next, it says, hey, so there's our nuclear symbol. We want to write our hyphen notation. So as a reminder on the spelling of fluorine, remember fluorine has the flu. If I had money for every time somebody misspelled fluorine, I would be a rich woman. So fluorine has the flu at the front of it. I then put a hyphen, and at the end of it, I put my mass number. So as we already said, that is 19. And that just tells us now the specific isotope of fluorine that we have. Rather than fluorine 17 or fluorine 18, I happen to have fluorine 19. Finally, it asks how many electrons and how many neutrons does this atom have? Well, for the number of electrons, we already said that protons and electrons are equal since it was an atom. So that means I have 9 of those. For my neutron count, I kind of have to do a little sneaky here. I know that I have a mass number of 19, which is protons plus neutrons. Well, if my proton count is 9, then I need something that would add to 9 to give me 19. So that means my neutron count here must be 10 for this particular element. All right, last but not least here, it says write the nuclear symbol for an ion that has 38 neutrons, 36 electrons, and a charge of -1. First off, we see it is an ion, so what that means is this will have a charge, and no longer can I assume that protons and electrons are equal. So I'm going to have to do a little bit of work here, okay? I also see that they didn't give me proton count, which is kind of a problem because that means I need to use this information to figure out exactly what element I have, exactly how many protons are there. And the way I'm going to do that is by comparing the number of electrons and whatever my charge is. If you remember, electrons have a negative charge. So this means I have 36 things that are negative. So in order to remain as a charge of -1, that means I need one more negative thing than I have positive things. So if I kind of use that to my advantage, I can say, well, to have one more negative thing, if I have 35 positive things, okay, that would still leave me with one more negative than I have positives. So what that means here is that my proton count is going to be 35. Now that I know that, I can now go figure out exactly what my element would be, by looking at my periodic table. So if I go look at my periodic table, I can see that bromine has an atomic number of 35. That's my proton count. And so I know that this element must be bromine. So now I can really start filling in some of this information here. As we already said, it has a charge of -1. On the bottom, I would put my atomic number, which is my number of protons, as we determined that's 35. And on the top, I would put my mass number. Now, again, as a reminder, mass number is protons plus neutrons together. So if I have 35 protons, I have 38 neutrons. 35 plus 38 would give me a grand total of 73. And so there's my nuclear symbol. So just a little refresher of all those protons, neutrons, electrons. I honestly kind of like doing these. They remind me of doing, I don't know, some sort of like little logic puzzle where it's like chemistry Sudoku, where I'm trying to figure out the number of everything that I have. All right, so flipping to the next page, we also want to go ahead and talk about average atomic mass, sometimes referred to as atomic weight. We do have average atomic masses on our periodic table, like for example here, hydrogen is this 1.008, or lithium is 6.94, beryllium's 9.01. And what those numbers are an average of all of the isotopes of that element found on Earth. So it says here a little bit more on isotopes. Isotopes will have the same number of protons but a different number of neutrons. So if they have a different number of neutrons, if you have an isotope, they'll have the same atomic number as each other, but they'll have a different mass number. And so what happens is that an element could have several different stable isotopes that are found on Earth. There's only a couple elements that only have one stable isotope. I've given you a few of them here. Aluminum, fluorine, and phosphorus only have one stable isotope. But most elements have at least 2 or 3. There's even some that have like 7 or 8 stable isotopes, especially some of the bigger elements. And so what scientists have done is they have gone and taken samples from all over the Earth and analyze them in what's called a mass spec machine, which we'll talk about in our next video, to kind of see like what percentages each of the isotopes are present in those samples. And so then what they've done is they've analyzed all these samples and they have done a weighted average of them to post those values on our periodic table for our atomic masses. Now, we have to be really careful because when we have these percentages and we have these masses, we can't just take a straight simple average. If I have 3 isotopes with 3 mass numbers, I can't just add those 3 together and divide by 3. It doesn't work like that. It has to be done with a weighted average. And so this formula might look familiar to you. Atomic mass is this crazy looking symbol. As a reminder, that is the sum symbol. Is the sum of the fraction abundance. So instead of a percent, I would change it over into fraction, which is just done by taking our percentage and dividing by 100. Or moving your decimal over 2 places, right? And then we multiply by the mass of the isotope. So each isotope, we take the fraction times the mass, and then we add it to the next fraction times the mass, and we add it to the next fraction times the mass. We sum all of those together for however many isotopes we have. If we have just 2 or 3, then we do it for those. If we have 8, then we would do it for all 8. And at the end of that, we will get a weighted average, something that tells us an average of those things based off of those percentages, okay? So to kind of see that as an example here, it says indium only has 2 stable isotopes, In-113 and In-115. Now you've noticed here they've given us some mass numbers, and then they've also given us a very specific atomic mass unit mass. Sometimes you'll see that. The reason why these don't perfectly match up to a mass number is because these AMUs are based off of using carbon-12 as kind of a reference standard. And what they've done is they've taken carbon-12 divided it by 12, the mass, and then kind of assigned that for all the other elements. And what happens is that the other elements have a different binding energy, and that creates some mass loss and sometimes some mass gain. There's a difference in masses that occur. So just keep in mind that if you see these exact AMUs, these exact masses, we want to use those instead of the mass numbers. But if you only have mass numbers, then that's fine to use, okay? It asks, which of these two isotopes do you think is more abundant, and justify your choice? Well, the first thing we need to do is we need to know what the average is for indium. And so I would go to my periodic table, and I see that indium, atomic number 49, has an average atomic mass of 114.82. So I'm going to write that down here, that its atomic mass is 114.82, according to the periodic table. So what that means is that the average of 112.904 and 114.904, the average of those two is coming out to 114.82. Now, look at that. This average is much closer to this 114.9 than it is to this 112.9. So what that means is that this indium 115 must be way more abundant because the average is closer to that number than it is to the other. I might have 90% of the indium 115 and maybe only like 10% of the indium 113 to get that average to be skewered so far over towards that one isotope. Obviously, you can do exact math with these, and that's what we're going to do next. Just to kind of give you a quick refresher on how to do a simple problem with average atomic mass. This gives us some information about some element that we don't know what it is. It gives us the isotope masses here, and so instead of giving us a mass number of protons plus neutrons, they've given us an exact mass, so we'll use that. And they've given us the percent abundances. Now, before I even work this problem, before I even do it and actually get my exact calculation, I already kind of know some information about this substance. I can already make a pretty good guess on where my average should be because I see that almost 79% of this substance is at 23.95 and only a little bit of it is at these other two values. So if I had to make a guess to where this average is going to come out, I would guess it's going to come out maybe a little bit higher than 23.95, but nowhere near these other two numbers. So I might be in like the low 24 point something range. Okay, so like I said, I already know some information here even without doing the calculation. Now, as far as doing the calculation, just as a refresher of how this works. Again, it is our fraction times our mass of each isotope added together. So for our first isotope here, since I have a percent, I would want to change that to a fraction. So again, I move that decimal over 2 places. So I'm going to use 0.7890 times my mass of 23.95 added to my next isotope. So instead of using 10%, I'm going to use 0.1. And I'm going to go ahead and write the zeros for sig fig purposes, but you wouldn't have to when showing your work. 24.95. And I'm going to add that to my last isotope. So I'm going to have 0.1110 once I move that decimal over 2 places. And then I'm going to have a mass of 26.95. So again, we already said that we know it should probably be closer to 24 than it is to 25 or 26. And if you actually go and plug this in your calculator, the value comes out to 24.38 atomic mass units. That ends up being our average atomic mass. So as we predicted, it ends up being closer to 24 than the other numbers. My advice to you, always double check your answer when you get it to see if it logically makes sense. You would be amazed the number of times I see people calculate these and they give me some random number like 12 and I'm like, but your masses are 23, 24, and 26. Like, how are you getting an average of 12 here? You can't. You must have plugged something in wrong. So please always ask yourself, does my answer make sense? Also, as far as sig figs, things get kind of sketchy here. So my advice is anytime you're doing an average atomic mass, always show 2 places past the decimal. If you notice on your periodic table that AP provides, we always see 2 places past the decimal with the exception of hydrogen. Don't ask me why on hydrogen they decided to show 3 places past the decimal. Who knows? But all the rest of them show 2. So as a general rule of thumb, I use 2 places past the decimal for average atomic mass. All right, last but not least here, we have kind of a trickier problem because this one where I'm actually trying to determine the percentages. It says the element europium exists in nature as 2 isotopes. 151 europium has a mass of 150.92 and 153 has a mass of 152.92. And then it gives us our average atomic mass. Calculate the relative abundance of each of these 2 isotopes. So I'm going to kind of start by plugging things in that I know into my formula, okay? I don't know my fractions yet because I don't know the percent abundances. So what I'm going to do is for now, I'm going to plug in X for my first isotope that has a mass, as it says, of 150.92. And I'm going to add that to my other isotope. Now, I have to be careful here because I have another fraction that I don't know. So I can't use X again because I've already used that as a variable. So here I'm going to use Y with a mass of 152.92. And that equals my average atomic mass of 151.96. Okay, now I know most of you that have taken algebra know that having 2 variables is a bad thing. Can't have 2 variables. So I got to kind of think about this logically here for just a minute. There's something else we know about X and Y. If you think back up to the previous problem and you look at those percentages, we all know that percentages should add to 100%. Well, if percentages add to 100%, then our fractions should add up to 1. And you can actually verify that by kind of looking at our numbers here, that 0.789, 0.1, and 0.111. Those would all add up to 1. So what that means here is that I also know that X plus Y equals 1. Now at this point, there's a couple different ways you can solve the algebra. One of the ways you can solve it is to solve for either one variable or the other, like you could solve for X, so X would be equal to 1 minus Y. And so then in for X, you could put in 1 minus Y, and then you could distribute everything and then consolidate terms and solve. Does that work? Absolutely. And if you want to do it that way, by all means, do it that way. I personally like to use the process of elimination. I think it's kind of fun to do, and I think it's a little simpler algebra-wise than substitution. That's just my 2 cents. But how it works is, as a reminder, I'm going to line up this equation with this one down here. I'm going to say X plus Y equals 1, okay? And what I want to do is I want to eliminate one of these terms, okay? So you can kind of pick. I'm going to personally eliminate Y out and leave behind X. So to eliminate Y out, if I'm going to combine these 2 equations together, I'm going to kind of sum them together here. If this is a positive 152.92Y, then I need a negative 152.92 times Y here. Now here's the key. Whatever I do to one term, I have to do to all the terms. So this term, this X, also has to be multiplied by that negative 152.92. This 1 also has to be multiplied by the negative 152.92. Now, any number multiplied by 1 is just that number, so I'm just going to put negative 152, excuse me. Whoa, there we go. 152.92 there. Okay. So now what I'm going to do is I'm going to kind of add up these 2 equations with each other, okay? So here, 150.92 minus 152.92 would leave me with negative 2, which are still multiplied by the X, okay? So again, I put the X at the end instead of the beginning, but it's the same difference, okay? Here, a positive 152.92y minus 152.92y ends up being 0, so plus 0. So I've effectively eliminated that term, okay? Here, 151.96 minus 152.92, combining that together would give me a negative 0.96. Okay, so next, what I want to do is I've got a negative 2x equals negative 0.96. I just want to solve for x. So that means I'm going to divide both sides by negative 2. And I end up getting that x is equal to 0.48. So there's our fraction that x would be. So now I'm going to use my noggin here. I got to be really careful and make sure that I put this with the correct isotope. I had x with the isotope that had a mass of 150.92, which was the europium 151. So that means the 151 europium has this as its fraction, which in a percent, moving that decimal over 2 places, would give us 48%. Yay! So let's talk about the other isotope. I don't have to go back and solve y. I can be kind of sneaky about this because I know that the fractions should add up to 1, as well as the percents should add up to 100%. So that means my europium 153 here must be 100 minus 48, which ends up giving me 52%. And there we go. We have successfully solved both of those percentages. So again, I like this elimination method. I think it's pretty easy to use. I don't know, personal preference, if you will. Hope this helps. And if you have any questions at all, please feel free to email me. Y'all have a good day, guys. Bye-bye.